Hello everyone, welcome to Malaysia Online Tuition YouTube channel. In this video, we are going to be looking at A-Level Probability and Statistics 1 Permutation and Combination Review Part 1. So if you like and enjoy watching this video, then please give us a thumbs up. If you want to receive updates on our newest video, then please hit that subscribe button as well as the notification bell so that you won't miss any of our future videos. So before we start, I would like to mention that we also offer online private tutoring for mathematics, physics, chemistry, and also biology. So for the first question here, given the digits 1, 2, 4, 5, 8, and 9, and none of the digits can be reused, for part 1, how many numbers which are less than 1000 can be formed using these digits? So for part 1 here, you can see that please be very careful, okay? They say less than 1000, meaning that it can be 1 digit. It can also be 2 digits, and of course, it can also be 3 digits. It cannot be 4 or more because less than 1000 meaning 999 or below. So now for the first case, we have 1 digit. So of course, for 1 digit, you have 1 space. So this is going to be what? 1, 2, 3, 4, 5, 6. So 6p1, and that is going to be 6. Okay, as you can see here, 6p1, you will get 6. Okay, so that is for 1 digit. So now for 2 digits, of course, you will be having 2 spaces. So since you have 6 of the digits and none of them can be reused, this is going to be 6p2. So what is 6p2? 30. And finally, for 3 digits, we are going to be having 3 spaces, and we have 6 digits to be chosen from, to be rearranged from. Okay, so we have 6p3. So what is 6p3? We get 120. So now you add all of them. So 120 plus 30, that is going to be 150, plus it is going to be 156. So this is the final answer for question number 1, part 1. For part 2, how many 4-digit odd numbers can be formed using these digits? Okay, so remember 4-digit but odd numbers. Okay, so now we have 1, 2, 3, and 4. Okay, 4-digit. So for odd numbers, meaning you can put at the last space there, okay, the behind one, 1, 5, and 9. So we can put 3 digits, so 1, 5, and 9. So after you put one of the digits behind here, okay, one of the odd numbers, then how many that you have left? You have 3 spaces that you want to rearrange, and then you have 5 digits left, okay, meaning 5p3. So the final answer for this one is going to be 5p3 times 3, okay, because this one, 5 digits left for 3 spaces. So for this one, 5p3 times 3. So we get 180 possible 4-digit odd numbers. So that's all for question number 1, part 2. So for part 3, how many possible arrangements of all the digits? Okay, remember, we need to use all the digits such that no 2 odd numbers are next to one another. Okay, so they said no 2 odd numbers. Okay, so we can write 6 spaces first. 3, 4, 5, and 6. So the first odd digit we can put, okay, this is not 0, okay, this is O. The first odd number we can put here. The second odd number we can put here. And the third odd number we can put here or here. Okay, so since none of the odd numbers or odd digits are repeated, we can just write 4 spaces that we can put the 3 odd numbers, so 4p3. So after we put the 3 odd numbers, we have 3 even numbers that we can rearrange. So that is going to be 3 factorials. Okay, just like that. 4p3, 4 spaces that we can put the 3 odd digits, and then the 3 factorials, we are rearranging the remaining 3 even digits. Okay, so then 4p3 times 3 factorials. So the answer is going to be 144 possible arrangements of all the digits, such that no 2 odd numbers are next to one another. Okay, so that's all for question number 1, part 3. Next, for question number 2, Annabelle, Bradley, Carrie, and 7 other friends are going to the theater. They are going to the theater using 2 5-seater cars of different make. Given that only Annabelle and Carrie cannot drive, and Bradley cannot be in the same car with Annabelle and Carrie, find how many ways can all of them be seated in the 2 cars. Okay, so for this question, we have 2 cars of different make. So you can imagine like, okay, the 5-seater cars, okay, usually the arrangement is going to be like this. Okay, 3 seats at the back, and then the passenger seat, and then the driver seat. Okay, so let's call this to be the car H, and the other car we can call it to be T. Okay, so now we know that Annabelle and Carrie cannot drive. So the other 8 friends, okay, including Bradley, they can drive. Okay, so since Bradley cannot be in the same car with Annabelle and Carrie, so for the first case, okay, for the first case, we can say that Bradley in H. So Annabelle and Carrie in T, okay, meaning in car T. So how many ways can Bradley be seated in car H? Okay, so you have to understand here. Since Bradley can drive, meaning Bradley can sit in any of these 5 seats, meaning including the driver's seat lah. Okay, so we can say that for the first case, 5. Okay, this 5 stands for where Bradley can sit in the car H, and then for Annabelle and Carrie in car T, they can sit anywhere except the driver's seat. Okay, so we can say 4P2. 1, 2, 3, 4. Okay, there are 4 seats available for Annabelle and Carrie, and we just want to put the 2 of them, right? So that's why 4P2. So the last one, for the rest, 7 friends, okay, no restrictions for them, okay, and all of them can drive. That's why we can put 7 factorials, okay, meaning we can put any of the 7 friends in any of car H or car T, no problem, because the restrictions only for Annabelle, Bradley, and Carrie. Okay, so that's the first case. So for the second case, you know that Bradley can be in car T. Okay, Bradley in car T and Annabelle and Carrie in H. So the same thing, okay, we are going to have 5, meaning Bradley can sit in any of the 5 seats, including the driver's seat. And in car H, Annabelle and Carrie can only sit in the 4 seats here, okay, except the driver's seat. So now we can have 4P2 again. And for the remaining 7 factorials, okay, meaning the other 7 friends, no restriction for them, 7 factorials. So the answer that we have here, we just multiply by 2 because the second case is just the same with the first case. So what's the answer? 5 times 4P2 and then times 7 factorials. So what do we get? 302,400. So we can write 2 times 5 times 4P2 times 7 factorials. So finally, we multiply this by 2. We get 604,800. So this is the final answer for question number 2. Now for question number 3. How many ways of rearranging the 7 letters in the word amazing if, for part 1, all consonants are together and all vowels are together? So for part 1, we can write the 7 spaces first. 3, 4, 5, 6, 7. So the consonants we have 1, 2, 3, 4. M, Z, N, and G. So none of them are repeated. And then for the vowels, we have A, I, okay? The A is repeated, okay? We have 2 A's. So after we make them into like a group of consonants and a group of vowels, then we will have 2 spaces left after. So now, for the consonants, like I said, we don't have any repeated consonants. So that is going to be 4 factorials. They can rearrange themselves inside the group. And then for the 3 vowels, we have 3 factorials. But remember, since we have repeating A, okay, we have 2 A's just now, we are going to be dividing by 2 factorials. And finally, the last 2 factorials is because we can have the group of vowels on the left and group of consonants on the right, or we can also have the group of vowels on the left, group of consonants on the right. Okay, so meaning that we can rearrange the group of vowels and consonants. That's why we have the last 2 factorials. So we can cancel this. And then the final answer is going to be 4 factorials times 3 factorials. So we get the final answer to be 144. So that's all for question number 3, part 1. For part 2, the 2 A's are at both ends. Okay, so again, we can write the 7 spaces. 3, 4, 5, 6, 7. So amazing, right? So we have 2 A's. So we can only put the 2 A's at both ends. So since they are the same, so it will be like 2 factorials divided by 2 factorials. Okay, so there is no difference whichever A that you put, okay, on both ends. Doesn't matter. So now we have 5 spaces left that we need to rearrange the 5 remaining letters. So we don't have any of the remaining 5 letters to be repeating. So that's why the answer is a straightforward 5 factorials, which is going to be 120. That's it. Okay, you can check. 5 factorials is going to be 120. Okay, so that's all for question number 3, part 2. And for the last one, how many ways of rearranging 3 of the letters in the word amazing if there must be at least one vowel? Okay, so remember they said one vowel. They didn't say at least one A, okay? One vowel. As long as it is a vowel, okay? So for the last one, we can call this the third part, okay? So we can first write a table. So it will be like vowels and consonants. Okay, so for the vowels, the vowels can be like A, or it can be also I, it can be 2 A's, 2 A's, 1 I, 1 A, 1 I, okay? So instead of writing V, we can write A, I, and then others, okay, like this. Better like this. Even though, yeah, we know that both the A and I, they are going to be vowels, right? Okay, so we can start with 1A and then 0I. So since we want 3 letters, so others must be 2, like that, okay? So then we can also have 2A and then 0I and 1 others. We can also have 0A, 1I, and 2 others. We can also have 2A, 1I, and 0 others. Okay, so we don't have any other cases other than this 4, because you can see that at least we want one vowel at least, right? So 1A here and then 1I here, so that is at least one already. So we can have 2. Okay, oh yeah, I think there is one more. Oh yeah, there is one more. I forgot. There is one more case. 1A, 1I, 1 others. Okay, very important for you to be able to get all the cases correctly. Okay, without missing any one of them or adding an unnecessary case. Okay, so now let's find out. Okay, so we don't have to consider the combination of A. Okay, so you just have to consider the others. Okay, the others meaning the consonants. We have 4 consonants. So we just have to write 4C2. And then this one, 4C1, 4C2, 4C0, and finally 4C1. That's it. Okay. So what is 4C2? That is going to be 6. So 4C1 is 4. 6, 4, 6, 1. Okay. 4C0 is 1. Okay. 1 and finally 4. So what is the total here? 6, 4, 10, 10, 16, 17, 21. Okay, so there are 21 ways of choosing. But remember, just now, if you look at the question, they say rearranging. Okay, so this is we need to do. Okay, but I forgot to consider the rearranging part. Meaning that aside from the combination that we have to rearrange them. Okay, so let's erase this again. Erase this. Okay, so we need to rearrange them. So when you have 1A and 2 others, okay, meaning that all of them are unique, meaning we don't have any repeated letters, we can say times 3 factorials. That's the only difference, okay? So 6 times 3 factorials, 3 times 2, yeah, 6. Okay? All right. And then for C1, okay, so as you can see here, you have 2A. So this is repeated letters. So times 3 factorials over 2 factorials. Okay, 4 times, okay, so what is this? 3 factorials divided 2 factorials is 3. 4 times 3. Done. So 0A, 1I, 2 others, no repeated letters. So you multiply by 3 factorials straight away. So this is 6 times 6. 4C0, okay, because you can see you have 2A, 1I. So this is just times 3 factorials over 2 factorials. So this is 1 times 3. Okay. And finally, 4C1, okay, meaning, 1A, 1I, 1 others, meaning that none of them repeating. So 3 factorials. So this is 4 times 6. Okay. 36, 12, 36, 3, 24. What is this? Okay, I think better use calculator lah, okay. 36 plus 12 plus 36 plus 3 plus 24, and then we have 111 to be the final answer. Okay, so this question you can see it combines combination as well as permutation, meaning you have to rearrange after you have chosen the 3 letters out of the 7 in the word amazing. So that's all for question number 3, part 3. Moving on to question number 4. In how many ways can a committee of 4 men and 3 women be seated in a row if for part 1, one particular man is the chairman and must be seated in the middle, and there is no other restrictions? So for part 1, we have 4 men and 3 women, meaning we have 7 spaces. 4, 5, 6, 7. So one particular man is the chairman, meaning that we already know who is the chairman. We don't need to select that chairman anymore. So we can put the chairman in the middle here, C. So we don't have to rearrange him. So that's why 1 only. And then 1, 2, 3, 4, 5, 6. Okay, so we have 6 spaces left to be rearranged out of 6 people, meaning we have 3 men and 3 women. So that is just a straightforward 6 factorials. Okay, so what is this? 6 factorials, the answer is 720. So this is the final answer for question number 4, part 1. Next, for part 2, one of the men is selected as the chairman and must be seated in the middle, and 2 particular women cannot be seated on the same side, okay, or refuse to be seated on the same side. So again, 7 spaces. But you can see, right, the difference between this question and the previous question. For the previous question, one particular man is the chairman, meaning that we have selected the chairman already. Okay, but in this question, part 2, one of the men is selected as the chairman and must be seated in the middle. Okay, so no difference in the arrangement, but we have a combination here because we need to choose the chairman from the 4 men available. So that means we have 4C1. Okay, and then like I said, the arrangement doesn't matter because this particular man, after being selected as the chairman, must be seated in the middle. So no arrangement problem. Okay, so now for the next condition or restriction, 2 particular women cannot be seated on the same side. Let's call them to be A and B. So for the first case, okay, we have A, for example, to be seated on the left side of the chairman and B to be seated on the right side of the chairman. So we want to rearrange A in one of the 3 seats. So we can say 3P1. Okay, 3P1. And the same thing for B. B can sit in any of the 3 seats to the right of the chairman. So again, 3P1. Okay, and another thing that we need to consider is that, okay, both of them can interchange, meaning that A sits on the left, B sits on the right, or it can also be that B sits on the left, A sits on the right. Okay, so later we need to multiply everything by 2. Okay, but later lah. Okay, because now before we write the multiply by 2 here, like this, we need to consider the remaining 4 people. Okay, because we know that we already consider the arrangement of the chairman in the middle, the 2 particular women. So now for the 4 remaining people, no other restrictions. So 4 factorials. Just like that. Okay. So what's the answer here? 4C1 is 4. 3P1 is 3. Times 4 factorials and then times 2. So the final answer is 1728. So that's all for question number 4, part 2. And finally for part 3 there. In how many ways can a committee of 4 people be selected from 4 men and 3 women if there must be more men than women? So whenever you have this kind of question where they say more men than women or women more than men, okay, you start straight away with the table. Okay. So when they say we want 4 people and men must be more than women, we can start with 4 men and 0 women. Okay, because we have 4 men and we want to select 4 people. So it is possible that we select all of them to be men. And then we can also have 3 men and 1 woman. 1 woman. But we cannot have 2 men and 2 women because this is not more men than women. So there are only 2 possible cases, 4, 0 and 3, 1. So what is this? 4C4 times 3C0. And for the next one, 4C3 times 3C1. Okay, 4C4 is 1, 3C0 is 1, so it's just 1. 4C3 is 4, 3C1 is 3, so that is 12. So 1 plus 12, that is going to be 13. Okay, so that's all for question number 4, part 3. Finally, this is question number 5, which is the last question of this video. 4 families, the Kumars, the Hassans, the Lims, and the Johns go to the convention center to see an exhibition. Mr. and Mrs. Kumar bring their 2 daughters, Mrs. Hassan brings her son, Mr. and Mrs. Lims do not bring any of their 2 children, any of their children, and Mr. John brings his son and daughter. There are 11 seats in a single row for them to be seated. For part 1, how many ways can all of them be seated if there are no restrictions? So no restrictions, we have 11 seats, okay, and 11 people. So straight away 11 factorials, okay, just that. So what is this? 11 factorials, that is going to be 39,916,800. Okay, so this is the final answer for question number 5, part 1. For part 2, how many ways can they be seated if not all of the children can be seated next to each other? So be careful of this word. Not all of the children can be seated next to each other. So when they say if not all, meaning that some of them can be, some of the children can be seated next to each other as long as not all of them. So the best way for you to tackle this kind of question is to use the complementary method. Okay. So meaning that now what you are going to find is you are going to find the number of possible ways that they can be seated if all of the children seated next to each other, meaning they are going to be in a group. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh yeah, I forgot. We need to count how many adults do we have and how many children do we have. Mr. and Mrs. Kumar 2, Mrs. Hassan 3, Mr. and Mrs. Lim 5, Mr. John 6. Okay, so 6 adults, 2 daughters, son and daughter, so 5 children. Okay, so we have 5 children, so we need to take 5 spaces. 1, 2, 3, 4, 5. Okay, so this is going to be the group of children. And then after we consider them to be in a group, 1, 2, 3, 4, 5, 6, 7. 7 spaces left. Okay, one of them being the group of children. 1, 2, 3, 4, 5, 6, 7. So for the 5 children, they can rearrange themselves in the group. So that is going to be 5 factorials. And then for the remaining 7 spaces, okay, which are the adults, the 6 adults and the group of children, that is going to be 7 factorials. So what is this? 5 factorials times 7 factorials, we get 604,800. Okay, so remember that this is what we don't want. So now what we need to do is we need to take the total from part 1, which is 11 factorials minus 604,800. Okay, so what is this? So 11 factorials minus answer, we get 39,312,000. Okay, so this is the final answer for question number 5, part 2. Last but not least, for the last part, part 3, given that there must only be adult men at both ends and the other adults cannot be seated next to another adult, how many arrangements are possible? Okay, so 11 spaces, 4, 5, 6, 7, 8, 9, 10, 11. So at both ends, we can only have adult men. So we have how many adult men? Okay, so Mr. Kumar, Mr. Lim, and Mr. John. So we have 3. But we want to rearrange only 2 of them. That's why we are going to write 3p2. Okay, and then after that, where can we put the remaining adults? Okay, so this is adult men. So the next adult can be here. The next one can be here. The next one can be here. And the next one can be here. As you can see, we have 4 remaining adults after we have put the 2 adult men at both ends. So now, 1, 2, 3, 4. We have how many adults remaining? 4. So we want to rearrange them in these 4 spaces. So 4p4 lah. So that is 4 factorials. And then for the children, no restrictions. So 5 factorials. Okay, just like that. So what is this? So 3p2 for the 2 adult men. Okay, we have 3 of them. So 3p2, 6 times 4 factorials, which for the remaining 4 adults. And then times 5 factorials. Okay, these are for the remaining 5 children. So 17,280 possible arrangements. Okay, so this is the final answer for question number 5, part 3. And that's all for this video of permutation and combination review part 1. So if you have any question or any comment, please leave them in the comment section below. So if you like and enjoyed watching this video, then please give us a thumbs up. If you want to receive updates on our newest video, then please hit the subscribe button as well as the notification bell so that you won't miss any of our future videos. Thank you very much for watching this video, and finally, please take care, and I hope to see you in our future videos.